Hello everyone! As promised, I'm going to be going over these water potential problems so that it hopefully makes some sense of what we are talking about in this class during this section of Unit 2. And so I'm going to go through my thought process. I'm going to do some drawing, some doodles to help really visualize what's going on here. And so let's look at what's given to us so far. We know our formula for water potential, which is water potential is equal to solute potential plus pressure potential. Next, we're going to have our formula for solute potential, which is negative ICRT. We are given our ionization constant, not our ionization constant, our pressure constant, my apologies. And we're given the conversion equation for Kelvin. Also, one last thing, two more things. We have our ionization constants for sucrose, which is 1, glucose, which is 1, and for salt, which is 2. When we talk about the pressure potential of pure water, we're going to give it a value of 0. And if we're talking about a plant cell going through turgor pressure, it's going to be 1. And so let's just jump straight into it. So if a cell's pressure potential is 3 bars and its solute potential is negative 4.5 bars, what is resulting water potential? So that's pretty easy. We're just going to jump in and use our water potential formula. We're going to plug in these values. So water potential is going to equal 3 bars plus negative 4.5 bars, which will give us a water potential of negative 1.5 bars. Cool, that was super easy. Now let's jump into the second one. The cell from question 1, so this was the cell, this was the water potential of the cell that we're talking about, is placed in a beaker of sugar water with a solute potential of negative 4.0. Which direction will the net movement of water be? Okay, so we need to draw this out to visualize this. So I'm going to do this in blue. So I'm going to draw myself a cup of water, or a solution, my apologies, a solution. I'm going to cup of a solution. Inside my solution, we're going to have a cell, which is from the first problem, which is going to have a negative 1.5 water potential. And our outside is going to have negative 4.0. So an important thing to note is that water, H2O, will always move from an area of low concentration to an area of high concentration. Forgot the most key word. Water will always move from an area of low concentration of solutes to an area of high concentration of solutes. Okay, so we're looking at our cell. Our concentration of solutes is negative 1.5 inside the cell, whereas the concentration of solutes outside of the cell is negative 4.0. And so what we're going to see is the movement going out from low to high. So water, the answer would be H2O, will flow out of the cell. And I'm going to add one more thing. This solution is hypertonic. Because water is moving out of the cell into the environment, like with the snail example. When you put a piece of salt on a snail, there's my snail. When you pour some salt onto it, our water is going to move out of the snail. Okay, next question. The original cell from question 1 is placed into a beaker of sugar water that has a solute potential of negative 0.5 megapascals. In which direction will water flow? Okay, so we have negative, let's highlight this, solute potential of negative 4.5 megapascals. But our previous answer up here, this is in bars. And so we have to do a little bit of conversion first. You could do it one way or the other. I'm going to go from megapascals to bars. So we have negative 0.15 megapascals. We're going to multiply this by 10 bars over 1 megapascal. It's like a little bit of stoichiometry. We're going to cancel out these units. Negative 0.15 times 10 is going to be negative 1.5 bars. So now let's visualize this again. So the inside of our original cell, negative 1.5, whereas the outside is going to be 1.5. And so if our concentrations are equal on the inside to the outside, then our solution is going to be isotonic. Someone drew this in red. Isotonic. And there is no net movement. There's no net movement of water. Okay, now number 4. The value of potential in a water potential in a root tissue was found to be negative 3.3 bars. So I'm going to highlight that. Negative 3.3 bars of root tissue. If you take that root tissue and place it into a 0.1 molar solution of sucrose at 20 degrees Celsius in an open beaker, what is the water potential of the solution? In which direction is this going to flow? Okay, so we're going to have to do some math here. So we need to figure out the we need to figure out the solute potential of the solution. So we're going to do the solute potential is going to equal negative ICRT. Since we are talking about sucrose, our I is going to equal it's going to equal 1. Our molar concentration is right here, 0.1 in moles. Our constant is going to be 0.0831. Normally, you're supposed to be doing putting in your units. I'm doing a really bad job of it at being a good example, but I'm not because I'm lazy. But you should do that. You should actually do this when you're taking your test. And then our last part, temperature, which is going to be 20 plus 273, which will give us 293 degrees Kelvin. So you'll do that math, you'll plug and chug, and you're going to get a solute potential of negative 2.43 bars. Okay, so we have that. If the value for the water potential in a root tissue is at negative 3.3, what direction will water flow? Okay, so we need to put this into a container. Blue. A container with a solution. We're going to have our cell, which is negative 3.3. And then our solution is, what is it again? Negative 2.43. And so what we're going to see is that our water is actually going to flow from an area of low to an area of high. An area of low concentration of solutes to an area of high concentration of solutes. And so it's going to move inward. So our solution is going to be hypotonic. Let's do this in orange. Hypotonic solution. H2O will flow in. Cool. Next question. NaCl dissociates into two particles with Na plus and Cl minus. If the solution in question 4 contained 0.1 millimeters instead of 0.1 moles of salt instead of 0.1 moles of sucrose, what is the water potential instead? Okay, so we have to do this formula again for solute potential. Let's do this in red. Solute potential is equal to negative ICRT. So this is going to be equal to negative, since we're talking about salt, our ionization constant is going to be 2. Our molar concentration is going to be the same. Our ionization constant is going to be the same. And our temperature is going to be the same. Oh, not equal. Times 293 K. So we'll do that math, and we're going to get a value of negative 4.87, twice the amount of this, of our original number up here. Bars. Oh, bars. Let's put it in a solution. I'm just going to copy this. No, I can't copy that. Okay, I'm going to green, not purple, green. Zoom in. So it was negative 3.3. And then the outside is going to be blue, and that's negative 4.487. It's going to move from an area of low concentration to high of solutes, keyword of solutes, I keep forgetting. It's going to move from inside the cell to the outside. So it's going to be hypertonic.